Hello there, and welcome to the Sleepy Science Society. Tonight, we are drifting outward from our small blue world, sailing gently through the vast darkness, exploring the family of worlds we call our solar system. This is a place both familiar and strange, where rocky spheres circle endlessly beside giants made of gas, where icy moons hide secret oceans, and where ancient rocks carry the memory of our beginning. As you settle in for this journey, imagine yourself floating weightless among the planets, watching them turn in their silent orbits, feeling the pull of gravity that binds everything together. If you enjoy these quiet explorations of the cosmos, I invite you to like, subscribe, or share a thought below. It helps other curious minds find their way here, one sleepy soul at a time. But for now, all you need to do is rest. Let your shoulders drop. Allow your breathing to slow. Let your mind drift gently into the endless night, and let's begin our journey home through the solar system. Our solar system began not with light, but with darkness. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a giant molecular cloud of gas and dust began to collapse under its own gravity. This cloud, stretching across several light-years of space, was composed mostly of hydrogen and helium, the primordial elements forged in the first moments after the Big Bang, mixed with heavier elements created inside dying stars that had exploded long before. Something disturbed this cloud. Perhaps a nearby star reached the end of its life and erupted in a supernova, sending shock waves rippling through space. Perhaps it was simply the slow, patient pull of gravity gathering the cloud inward. Whatever the trigger, a portion of this immense cloud began to fall in on itself, spinning as it collapsed, like a dancer pulling their arms close to spin faster. As the cloud contracted, it began to rotate more rapidly, and the spinning motion flattened it into a disk. Most of the material fell toward the center, where pressure and temperature climbed higher and higher. At the heart of this collapsing cloud, the proto-sun was being born. The outer regions of the disk, cooler and less dense, would become the birthplace of planets. This process, known as the nebular hypothesis, was first proposed centuries ago by philosophers who looked at the orderly motion of the planets and wondered how such a system could have formed. Immanuel Kant developed the theory in 1755, and Pierre-Simon Laplace independently proposed a similar model in 1796. They imagined that the solar system condensed from a rotating cloud, and though their ideas faced skepticism for many years, modern observations have confirmed their essential vision was correct. Within the swirling protoplanetary disk, tiny particles of dust began to stick together through static electricity and gentle collisions. These microscopic grains, smaller than sand, were the haoma, first solid material to condense from the cooling gas. In the hottest regions, close to the forming sun, only materials with extremely high melting points could solidify. Metals and rocky minerals condensed here, while lighter materials like water and methane remained as gas. Farther out, where temperatures were lower, ice could form, and the building blocks of planets grew larger and more numerous. The process of accretion had begun. Dust grains stuck together to form pebbles. Pebbles collided and merged into boulders. Boulders accumulated into mountain-sized bodies called planetesimals, and planetesimals, through countless collisions over millions of years, grew into planetary embryos. At the center of the disk, the proto-sun continued to grow, pulling in more and more material. The pressure at its core climbed until it reached a critical threshold. Hydrogen atoms, pressed together with unimaginable force, began to fuse into helium, releasing tremendous energy. Nuclear fusion ignited, and the sun was born, beginning to shine with the light that would illuminate the solar system for billions of years. The young sun was turbulent and active, producing powerful stellar winds that swept through the inner solar system like a cosmic broom. This phase, known as the T Tauri stage, cleared away most of the remaining gas and small particles from the inner regions, leaving behind only the larger bodies that had already formed. The early solar system was a violent place. Planetesimals crashed into one another with devastating force. Some collisions shattered bodies into fragments. Others merged them into larger masses. The planets grew through this chaos, each impact adding material and energy. The heat from these collisions was so intense that the young planets were molten, their surfaces glowing red in the darkness. Over time, the larger bodies swept up most of the debris in their orbital paths, and the bombardment began to ease. But even after the planets had mostly formed, a period of heavy bombardment continued for hundreds of millions of years. The surfaces of the inner rocky worlds were pounded by impacts, their faces scarred with craters that still remain today as ancient records of this violent era. The formation of our solar system was not instantaneous. It unfolded over tens of millions of years, a process both gradual and catastrophic. Scientists have dated meteorites, the primitive rocks that never became part of planets, and found they all share the same age of about 4.6 billion years, confirming when the solar system began. These ancient stones carry within them the chemical signatures of the stellar explosion that preceded our sun, the supernova that enriched the molecular cloud with heavy elements. In a profound sense, we are children of that long-dead star, built from its scattered remains. At the heart of our solar system, dominating it with overwhelming gravitational presence, burns the sun. It is not merely the largest object in the solar system. It is almost the entire solar system. The sun contains about 99.86% of all the mass in the solar system, with all the planets, moons, asteroids, and comets together making up barely more than 0.1%. This massive sphere of plasma, more than 100 times wider than Earth, is the gravitational anchor that holds everything else in orbit, the engine that drives weather and climate on the planets, and the source of nearly all the energy that flows through our corner of space. The sun is made almost entirely of hydrogen and helium, the simplest and lightest elements in the universe. At its surface, temperatures reach about 5,500 degrees Celsius, hot enough to vaporize any known substance. But this is cool compared to the interior. Deep in the sun's core, where the pressure is millions of times that of Earth's atmosphere, temperatures soar to about 15 million degrees Celsius. Under these extreme conditions, hydrogen nuclei move so fast and come so close together that they overcome their natural repulsion and fuse into helium. This nuclear fusion releases energy in the form of light and heat, and that energy slowly works its way outward through the sun's layers. The journey of energy from the core to the surface takes an extraordinarily long time. A photon of light created in a fusion reaction in the core might take tens of thousands of years to reach the surface, bouncing endlessly off of particles, absorbed and re-emitted countless times as it struggles outward through the dense interior. Finally, it escapes into space, streaming away at the speed of light. 8 minutes later, a tiny fraction of that energy reaches Earth, warming the surface, driving winds and ocean currents, powering photosynthesis in plants. The light that falls on your face when you step outside on a sunny day began its journey in the sun's core long before recorded human history. The sun's surface, called the photosphere, is not solid but a roiling sea of plasma, with hot gas rising from below and cooler gas sinking back down in constant convection. Dark spots appear on the surface, cooler regions where strong magnetic fields suppress the convection. These sunspots come and go in an 11-year cycle as the sun's magnetic field strengthens, twists, and then resets. Above the photosphere lies the sun's atmosphere, a realm of increasing strangeness. The chromosphere glows with a reddish light during eclipses, and beyond that stretches the corona, the sun's outer atmosphere. The corona is a puzzle that has intrigued scientists for decades. Despite being farther from the core, the corona is paradoxically much hotter than the surface below it, reaching temperatures of millions of degrees. NASA's Parker Solar Probe has directly observed magnetic reconnection in the sun's atmosphere, helping to solve this 70-year mystery of how the corona becomes so hot. From the corona, a continuous stream of charged particles flows outward in all directions. This is the solar wind, a plasma that races through the solar system at hundreds of kilometers per second, carrying the sun's magnetic field with it. When the solar wind reaches Earth, it interacts with our planet's magnetic field, creating the beautiful auroras that dance across polar skies. But the solar wind extends far beyond Earth, creating a vast bubble called the heliosphere that surrounds the entire solar system, shielding it from some of the harsh radiation of interstellar space. The boundary where the solar wind finally slows and mingles with the interstellar medium lies far beyond the orbit of Neptune, in the distant reaches where the Voyager spacecraft now travel. The sun is not eternal. It has been shining for about 4.6 billion years, and it will continue for roughly another 5 billion years. As it ages, it will gradually brighten, and eventually it will exhaust the hydrogen fuel in its core. When that happens, the core will contract and heat up, while the outer layers will expand enormously. The sun will become a red giant, swelling until it may engulf the inner planets. Earth, if it survives, will be a scorched, lifeless rock in the outer atmosphere of a dying star. Finally, the sun will shed its outer layers into space, creating a beautiful planetary nebula, and leave behind a dense, slowly cooling remnant called a white dwarf. But that end is unimaginably far in the future. For now, the sun burns steadily, the stable heart of our solar system. Closest to the sun, baked by its relentless heat, orbits the smallest of the 8 major planets. Mercury is a world of extremes, a place where temperatures swing from scorching heat to bitter cold in the span of a single day. With a diameter only slightly larger than Earth's moon, Mercury is a dense ball of rock and metal, its surface pounded by billions of years of impacts into a landscape that resembles the moon's cratered highlands. Wrinkles on Mercury's surface suggest the planet has been shrinking for most of its lifetime as its interior cools, causing the crust to contract and buckle. Mercury has no atmosphere to speak of, just a thin exosphere of atoms knocked off the surface by the solar wind and micrometeorite impacts. Without an insulating blanket of air, the side facing the Sun heats to about 430 degrees Celsius, hot enough to melt lead, while the night side plunges to minus 180 degrees Celsius. Mercury rotates slowly, taking 59 Earth days to complete one rotation, and it takes 88 Earth days to orbit the Sun. This creates a strange relationship, where a single day on Mercury, from sunrise to sunrise, lasts 2 Mercurian years. The planet's proximity to the Sun and its slow rotation make it a challenging world to observe, always appearing close to the Sun in Earth's sky, never venturing far from the glare of our star. Beneath Mercury's cratered surface lies a surprise. The planet has an unusually large metallic core, making up about 60% of its total mass. Scientists think that early in the solar system's history, a massive collision may have stripped away much of Mercury's rocky mantle, leaving behind the disproportionately large iron core. This core generates a weak magnetic field, a faint echo of Earth's powerful magnetosphere, but enough to create a small bubble that deflects some of the solar wind. Moving outward, we come to Venus, Earth's nearest planetary neighbor, and a world often called Earth's twin because of their similar sizes. But Venus is a twin only in dimensions. In almost every other way, it is a vision of hell. Hidden beneath thick clouds of sulfuric acid lies a surface hotter than Mercury's, even though Venus orbits much farther from the Sun. The reason is a runaway greenhouse effect. Venus's atmosphere, 90 times denser than Earth's, is made almost entirely of carbon dioxide, an extraordinarily effective greenhouse gas. This thick blanket traps heat so efficiently that surface temperatures reach about 470 degrees Celsius, hot enough to melt lead and render the surface a dim, red-lit wasteland where no liquid water can exist. The clouds of Venus are made of sulfuric acid droplets suspended in the carbon dioxide atmosphere. They are so thick and reflective that they make Venus the brightest planet in Earth's sky, shining like a brilliant star in the evening or morning. But these clouds also hide the surface completely, and for many years, scientists could only speculate about what lay beneath. Radar observations and Soviet lander missions eventually revealed a landscape of volcanic plains, highland regions, and features that suggest recent geological activity. Scientists discovered in 2023 that Venus has thousands more volcanoes than previously realized, and many of them could still be active. The planet's surface appears to have been resurfaced by massive volcanic episodes in its past, erasing most of the ancient cratered terrain that would otherwise record its early history. Venus rotates incredibly slowly and in the opposite direction to most other planets. A day on Venus lasts longer than its year. The planet takes about 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun. Standing on Venus's surface, if you could survive the crushing pressure and searing heat, you would see the sun rise in the west and set in the east, and that single day would stretch across more than 100 Earth days. Why Venus rotates backwards and so slowly remains a mystery, though scientists think massive tidal effects from the sun and the thick atmosphere might play a role. Then there is Earth, our home, the only world we know with certainty that harbors life. From space, Earth appears as a fragile blue marble suspended in the blackness, its surface covered by oceans that hold most of the planet's water, its atmosphere a thin shell that looks impossibly delicate against the vastness of space. Earth is unique in the solar system for having liquid water on its surface, a consequence of its perfect distance from the sun and the presence of an atmosphere that maintains temperatures in the narrow range where water can exist as a liquid. This water, covering about 70% of the surface, is essential to life as we know it, acting as a solvent for chemical reactions, a medium for transporting nutrients, and a moderator of temperature. Earth's atmosphere is a mixture of nitrogen and oxygen, with traces of other gases including carbon dioxide and water vapor. Unlike Venus, where greenhouse gases ran wild, Earth has maintained a delicate balance for billions of years, with life itself playing a role in regulating the composition of the atmosphere. Plants produce oxygen through photosynthesis, and the oxygen we breathe is itself a biological product, created by countless tiny organisms over eons. Beneath the atmosphere, Earth's surface is restless. Tectonic plates drift across the surface. Continents collide and separate. Mountains rise and erode. This geological activity, driven by heat from Earth's interior, recycles the crust and helps maintain the conditions that support life. Earth has one large moon, simply called the Moon, which orbits at an average distance of about 384,000 kilometers. A study published in October 2023 revealed that the Moon is likely 40 million years older than scientists previously realized, based on analysis of tiny impact crystals in lunar rock samples brought back by Apollo missions. The Moon's gravitational pull creates the ocean tides, and its presence has helped stabilize Earth's axial tilt, preventing wild swings in climate that might have made life more difficult to establish. The Moon formed in a catastrophic collision early in Earth's history, when a Mars-sized body struck the young Earth, ejecting debris into orbit that eventually coalesced into our natural satellite. Beyond Earth orbits Mars, the red planet, a world that has captivated human imagination for centuries. Mars is about half the diameter of Earth, with a thin atmosphere composed mostly of carbon dioxide. The planet's distinctive red color comes from iron oxide, rust that covers much of its surface. Mars is cold, with average temperatures around minus 60 degrees Celsius, and its thin atmosphere provides little protection from radiation or insulation against temperature extremes. Yet Mars was not always this way. Evidence scattered across its surface tells a story of a warmer, wetter past. Ancient river channels cut through the Martian landscape. Deltas fan out where rivers once emptied into lakes or seas, and minerals that form only in the presence of liquid water are found in many locations. Billions of years ago, Mars likely had a thicker atmosphere and liquid water flowing across its surface. What happened? Mars lost its magnetic field early in its history, and without that protective shield, the solar wind gradually stripped away the atmosphere molecule by molecule over hundreds of millions of years. As the atmosphere thinned, liquid water could no longer exist on the surface. It either escaped into space or retreated underground, where some remains frozen in polar ice caps, and possibly as liquid aquifers beneath the surface. NASA's Perseverance rover discovered mudstones in Mars's Jezero crater in September 2025 that contain organic carbon and unusual textures hinting at possible biosignatures, adding to the tantalizing possibility that life might have emerged on Mars when conditions were more favorable. The search for past or present life on Mars continues to be one of the most compelling goals of planetary science. Mars has two small moons, Phobos and Deimos, irregularly shaped rocks that are likely captured asteroids. Phobos orbits so close to Mars that it is gradually spiraling inward, and in tens of millions of years, it will either crash into the surface or be torn apart by tidal forces to form a ring around the planet. Between Mars and Jupiter lies a region of space filled with rocky debris, the asteroid belt. This is not a densely packed field like in science fiction movies, but a vast zone where millions of rocky and metallic bodies orbit the Sun in the space that might have become another planet. The asteroids range in size from Ceres, a dwarf planet nearly 1,000 kilometers across, down to boulders and pebbles. Jupiter's rapid growth apparently prevented the formation of a planet in the gap between Jupiter and Mars. What remains is the asteroid belt, whose total mass is less than 1/3 the mass of the Moon. The gravitational influence of Jupiter stirred up the region, increasing collision velocities to the point where planetesimals shattered rather than merged, preventing them from accumulating into a single planet. The asteroids are incredibly diverse in composition. Some are made primarily of metal, likely the exposed cores of larger bodies that were shattered in collisions. Others are rocky, composed of silicate minerals, and still others are carbonaceous, rich in carbon compounds and organic molecules. These primitive asteroids have changed little since the solar system's formation, and they preserve clues about the conditions in the early solar nebula. Meteorites that fall to Earth, most of which come from asteroids, provide scientists with samples of this ancient material, allowing them to study the building blocks of planets directly. Ceres, the largest object in the asteroid belt, was reclassified as a dwarf planet in 2006 along with Pluto. It is round, shaped by its own gravity, but it has not cleared its orbital neighborhood of other debris, the criterion that distinguishes a full planet. Ceres is fascinating in its own right, with a surface covered in craters and bright spots that turned out to be deposits of salt left behind when water ice sublimated from beneath. There is evidence that Ceres has or had a subsurface ocean, making it another potential location where conditions for life might exist. Beyond the asteroid belt, we enter the realm of the giant planets, worlds utterly unlike the rocky inner planets. These are places where solid ground gives way to layers of liquid and gas, where storms larger than Earth have raged for centuries, and where moons the size of planets orbit in strange and wonderful dances. First among the giants is Jupiter, the king of planets, a world so massive that it contains more than twice the mass of all other planets combined. Jupiter holds the record for the most moons discovered around any planet in our solar system, boasting over 90 confirmed satellites. Jupiter is a gas giant composed mostly of hydrogen and helium, with no solid surface to stand on. If you could somehow descend through Jupiter's atmosphere, you would pass through layers of gas that gradually become denser and hotter. Eventually, the pressure would become so great that hydrogen would be compressed into a liquid, and deeper still, into a strange metallic form that conducts electricity. At the very center might be a rocky or icy core several times the mass of Earth, though this remains uncertain. The journey downward would be fatal long before reaching any core, as temperatures climb to tens of thousands of degrees and pressures reach millions of times that of Earth's atmosphere. Jupiter's atmosphere is a swirling canvas of bands and zones, light and dark stripes that wrap around the planet parallel to its equator. These bands are driven by powerful winds that blow in opposite directions in adjacent zones, creating turbulence at the boundaries. The most famous feature of Jupiter is the Great Red Spot, an enormous storm that has been observed for at least 350 years. This anticyclonic storm, rotating counterclockwise in the southern hemisphere, is larger than Earth, though it has been shrinking in recent decades. The winds at its edges reach speeds of several hundred kilometers per hour, and the storm shows no signs of dissipating anytime soon. Jupiter possesses an incredibly powerful magnetic field, the strongest of any planet in the solar system. This magnetosphere extends millions of kilometers into space, far enough to encompass some of Jupiter's moons. Charged particles trapped in this magnetic field create intense radiation belts that would be lethal to unshielded spacecraft and astronauts. The interaction between Jupiter's magnetic field and its moon Io creates spectacular auroras at Jupiter's poles and generates powerful radio emissions that can be detected from Earth. The 4 largest moons of Jupiter, discovered by Galileo in 1610, are worlds in their own right. The Galilean moons must have condensed from a circumplanetary disk billions of years ago, as evident from their coplanar orbits around Jupiter. Io, the innermost of the 4, is the most volcanically active body in the solar system. Tidal forces from Jupiter's gravity flex Io's interior, generating tremendous heat that erupts in spectacular volcanic plumes that shoot sulfur compounds hundreds of kilometers above the surface. The surface is painted in yellows, oranges, and reds from the sulfur, and there are no impact craters because volcanic activity constantly resurfaces the moon. Europa, the next moon out, is covered in water ice that forms a smooth, cracked surface crisscrossed by long linear features. Beneath this icy shell, scientists believe there is a global ocean of liquid water, kept warm by tidal heating similar to what affects Io, though less intense. Saturn's icy moon Enceladus, similar to Europa, has fascinated scientists with its spectacular water plumes, which NASA's Cassini spacecraft revealed contain organic molecules. Europa is one of the most promising places in the solar system to search for life beyond Earth. The ocean beneath the ice might have been stable for billions of years, and where there is liquid water, energy, and organic molecules, life might find a way. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It is the only moon known to have its own magnetic field, generated by a liquid iron core. Ganymede and Callisto are 50% water ice but presumably have rocky cores, perhaps of carbon or silicon. Ganymede has a varied surface with dark, heavily cratered regions and lighter areas with grooves and ridges, evidence of geological activity in the past. Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system, its ancient surface recording billions of years of impacts. It too might harbor a subsurface ocean beneath its icy crust. Beyond these four giant moons, Jupiter has dozens of smaller satellites, many of them irregular in shape and likely captured asteroids or fragments from past collisions. Researchers discovered 20 new moons orbiting Saturn and using the Subaru telescope, bringing Saturn's total moon count to 82 and surpassing Jupiter, though more recent discoveries have pushed Jupiter back into the lead with over 90 moons. Continuing outward, we arrive at Saturn, the jewel of the solar system, famous for its magnificent ring system. Saturn is another gas giant, similar in composition to Jupiter, but less massive and less dense. In fact, Saturn is the least dense planet in the solar system. If you could find an ocean large enough, Saturn would float. Like Jupiter, Saturn has no solid surface, just layers of gas transitioning to liquid, and possibly a small rocky core deep inside. The atmosphere displays bands and storms, though less prominent than Jupiter's, and a strange hexagonal cloud pattern exists at Saturn's North Pole, a geometric feature whose origin is still debated. The rings of Saturn are one of the most beautiful sights in the solar system. From a distance, they appear as smooth, solid disks, but they are actually composed of countless individual particles, ranging in size from dust grains to house-sized boulders, all made primarily of water ice. The rings are incredibly thin relative to their diameter, extending hundreds of thousands of kilometers across but only tens of meters thick in most places. They orbit Saturn in accordance with Kepler's laws, with inner particles moving faster than outer ones, creating waves and patterns as gravitational interactions with Saturn's moons sculpt the ring structure. The origin of Saturn's rings is uncertain. They might be the remnants of a moon that was torn apart by tidal forces or shattered in a collision. Or they might be primordial material left over from Saturn's formation. Scientists think the rings might be relatively young, perhaps only a few 100 million years old, because they are so bright and clean. Over time, dust from micrometeorite impacts should darken them, unless they are constantly renewed somehow. The rings will not last forever. They are slowly spiraling into Saturn, raining down onto the planet's upper atmosphere, and in perhaps 100 million years, they might vanish entirely. Saturn has an impressive collection of moons, more than 80 at the last count. The largest, Titan, is a world of profound interest. Titan is bigger than Mercury and has a thick atmosphere, the only moon in the solar system with a substantial atmosphere. This atmosphere is composed mostly of nitrogen, like Earth's, but it is denser and extends higher into space. Titan's surface is hidden beneath a thick haze of orange-brown clouds made of complex organic molecules. When the Cassini spacecraft arrived at Saturn and deployed the Huygens probe to land on Titan, it revealed a world with lakes and seas of liquid methane and ethane, rivers that carve channels through hills of water ice as hard as rock, and a hydrocarbon cycle that resembles Earth's water cycle. Titan is incredibly cold, with surface temperatures around minus 180 degrees Celsius, cold enough that water ice is as hard as granite and methane can exist as a liquid. Despite the cold, Titan has active weather, with methane rain falling from clouds and seasonal changes that cause the liquid to migrate between the northern and southern hemispheres. Beneath the surface, Titan is thought to have an ocean of liquid water mixed with ammonia, another potential habitat for life, though very different from Earth. Another of Saturn's moons, Enceladus, is a small, icy world that hides a remarkable secret. Enceladus has spectacular water plumes that NASA's Cassini spacecraft revealed contain organic molecules. These plumes erupt from cracks near the moon's south pole, shooting water and ice particles hundreds of kilometers into space. The source is a subsurface ocean beneath the icy crust, kept liquid by tidal heating from Saturn's gravity. The plumes contain not just water, but also salts, organic compounds, and even molecular hydrogen. Evidence of chemical reactions between the ocean and the rocky core. This makes Enceladus another prime target in the search for life. Farther out still lie the ice giants, Uranus and Neptune, two worlds unlike any others in the solar system. They are smaller than Jupiter and Saturn, but much larger than Earth, and their composition is different. While the gas giants are mostly hydrogen and helium, the ice giants are composed largely of heavier elements. The term ice giant refers to the presence of water, methane, and ammonia in their interiors, which at the high pressures inside these planets exist as hot, dense fluids rather than ice in the familiar sense. These materials, mixed with rock and some hydrogen and helium, give the ice giants their blue-green colors and distinct properties. Uranus is the oddball of the solar system because of its extreme axial tilt. Uranus has an extreme tilt of 97.77 degrees, so its poles consistently point toward the Sun during parts of its orbit. Essentially, Uranus rotates on its side, with its poles sometimes pointing almost directly at the Sun. This means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness, as Uranus completes its 84-year orbit around the Sun. Scientists think a massive collision early in Uranus's history knocked it onto its side, though this remains speculative. Uranus appears as a pale blue-green disk, with few visible cloud features. Its atmosphere is calm compared to the dynamic atmospheres of Jupiter and Saturn, though storms do occur. The color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green. Uranus has a faint ring system, discovered in 1977, and 27 confirmed moons. Astronomers using the James Webb Space Telescope uncovered a tiny new moon orbiting Uranus in August 2025, increasing the planet's moon tally to 29. The largest moons, including Titania, Oberon, Umbriel, Ariel, and Miranda, are named after characters from Shakespeare and Alexander Pope. Miranda has one of the most bizarre landscapes in the solar system, with a surface that looks like it was torn apart and reassembled, featuring towering cliffs and jumbled terrain. Neptune, the last of the major planets, is slightly smaller than Uranus but more massive, giving it a higher density. It is a dynamic, stormy world, despite being the farthest from the Sun and receiving the least solar energy. When Voyager 2 flew past Neptune in 1989, it revealed a planet with the strongest winds in the solar system, reaching speeds of over 2,000 kilometers per hour. Dark spots, large storm systems similar to Jupiter's Great Red Spot, have appeared and disappeared in Neptune's atmosphere. The planet's deep blue color comes from methane, like Uranus, but Neptune appears a richer, darker blue for reasons scientists do not fully understand. Neptune has 14 known moons, the largest of which is Triton. Triton is a captured moon, likely a large object from the Kuiper Belt that was gravitationally captured by Neptune early in the solar system's history. Triton is a prominent example of a captured moon in a retrograde orbit, moving opposite to Neptune's rotation. Triton is geologically active, with nitrogen geysers that erupt from beneath its surface, and it has a thin atmosphere. The moon is slowly spiraling inward toward Neptune, and in several billion years, it will either crash into the planet or be torn apart by tidal forces to form a magnificent ring system. Beyond Neptune lies the frontier of the solar system, a vast region of icy bodies orbiting in the cold darkness, far from the sun's warmth. This is the Kuiper Belt, a disc-shaped region extending from about 30 astronomical units from the Sun, just beyond Neptune's orbit, out to perhaps 50 astronomical units or more. 1 astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers, so the Kuiper Belt lies billions of kilometers from the Sun. The Kuiper Belt is home to countless small icy worlds, remnants of the early solar system that never accumulated into a planet. The most famous resident of the Kuiper Belt is Pluto, once considered the 9th planet but reclassified as a dwarf planet in 2006. The reclassification sparked controversy and public debate, but it reflected a more nuanced understanding of the solar system. Pluto is one of many large objects in the Kuiper Belt, and recognizing it as a dwarf planet acknowledges both its significance and the reality that it shares its orbital space with many similar bodies. Pluto is a complex world with a surface of nitrogen ice, mountains of water ice, and a thin atmosphere that freezes and falls to the surface as Pluto moves farther from the Sun in its elliptical orbit. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more geologically active and diverse than anyone expected. The spacecraft found a heart-shaped region of smooth plains, young in geological terms, with no impact craters, suggesting recent resurfacing. Mountains of water ice rise several kilometers high, and exotic ices of methane, nitrogen, and carbon monoxide coat different regions in varied colors. Pluto has 5 known moons, the largest of which, Charon, is so large relative to Pluto that the two are sometimes considered a binary system, orbiting a common center of mass located between them. The Kuiper Belt contains many other intriguing objects. Astronomers uncovered a massive new trans-Neptunian object in September 2025, designated 2017 of 201, lurking at the edge of our solar system with an orbit stretching 25,000 years. Other notable dwarf planets include Eris, which is about the same size as Pluto, and was one of the discoveries that prompted the reclassification of Pluto, and Makemake and Haumea, both of which have unusual properties. Haumea rotates so fast that it has been stretched into an elongated ellipsoid, and it has a ring system, the first discovered around a Kuiper Belt object. Even farther out, the scattered disk extends beyond the main Kuiper Belt. Objects in the scattered disk have highly elliptical and inclined orbits, likely scattered outward by gravitational interactions with Neptune during the early solar system's chaotic phase. Some of these objects venture far beyond the Kuiper Belt, spending most of their time in the distant cold before swinging back toward the inner solar system. Comets are among the most spectacular visitors to the inner solar system. These icy bodies originate in the outer reaches, either in the Kuiper Belt or, for long-period comets, from an even more distant region called the Oort cloud. The Oort cloud is a theoretical spherical shell of icy objects surrounding the solar system at distances up to 100,000 astronomical units or more, nearly halfway to the nearest star. The Oort cloud has never been directly observed because its objects are too small and too distant to see with current telescopes. But its existence is inferred from the orbits of long-period comets that plunge into the inner solar system from all directions. Comets are often described as dirty snowballs, a mixture of water, ice, frozen gases like carbon dioxide and methane, and rocky dust. When a comet's orbit brings it close to the Sun, the ice begins to sublimate, turning directly from solid to gas without becoming liquid. This gas, along with dust freed from the ice, streams away from the comet, pushed by the solar wind and radiation pressure. This creates the comet's distinctive tail, which can stretch millions of kilometers and always points away from the Sun, regardless of the direction the comet is moving. Some comets develop two tails, one of gas that appears bluish and one of dust that appears white or yellow. Famous comets like Halley's Comet return periodically to the inner solar system, their orbits altered by gravitational interactions with the planets. Halley's Comet has an orbital period of about 76 years, and has been observed and recorded by humans for over 2,000 years. Scientists may have solved the mystery in May 2025 of why the Moon shows ancient signs of magnetism, although it has no magnetic field today, and similar detective work with meteorites and comets continues to reveal clues about the early solar system. Comets might have delivered water and organic molecules to the early Earth, playing a role in the origin of life. Recently, astronomers have detected objects passing through the solar system that come from beyond, interstellar visitors on their way through our neighborhood. The first confirmed interstellar object, discovered in 2017, was initially thought to be an asteroid and named Oumuamua, a Hawaiian word meaning scout. Its strange, elongated shape and unexpected acceleration as it left the solar system sparked speculation, though most scientists think it was a comet with unusual properties. A second interstellar visitor, a comet designated Borisov, was discovered in 2019. Observations with the James Webb Space Telescope showed that the new interstellar comet 3Huayhui/Atlas is surprisingly rich in carbon dioxide. These visitors from other star systems offer a glimpse of the diversity of objects that exist throughout the galaxy. One of the most intriguing mysteries of the solar system is the possibility of an undiscovered ninth planet, sometimes called Planet 9, lurking in the outer darkness beyond the Kuiper Belt. This is not Pluto, which was the ninth planet before its reclassification, but a hypothetical massive planet that some astronomers believe might exist based on indirect evidence. The idea arose from observations of extreme trans-Neptunian objects, small bodies with orbits that extend far beyond Neptune. Several of these objects have orbits that appear to be clustered in a way that seems unlikely to occur by chance, as if their paths have been shaped by the gravitational influence of an unseen massive planet. If Planet 9 exists, it would be a super-Earth, perhaps 5 to 10 times more massive than Earth, orbiting the Sun at a distance of several hundred astronomical units, far beyond the Kuiper Belt. Its orbital period might be 10,000 to 20,000 years, and it would be incredibly faint, explaining why it has not yet been detected despite searches. The evidence for Planet 9 is indirect and statistical, and not all astronomers are convinced it exists. Alternative explanations for the orbital clustering have been proposed, including the collective gravitational influence of many smaller Kuiper Belt objects, or observational bias in how trans-Neptunian objects are discovered. The search continues, with new surveys scanning the sky for a faint moving point of light that would reveal this hidden giant. As we drift through this tour of the solar system, it becomes clear that our corner of the universe is far more diverse and dynamic than early astronomers could have imagined. The solar system is not a static collection of objects frozen in place. It is a living, evolving system where moons hide oceans beneath their icy crusts, where storms larger than continents rage for centuries, where comets carry the building blocks of life, and where new moons and distant objects continue to be discovered, rewriting our understanding with each finding. The exploration of the solar system has been one of humanity's great adventures. From the first telescopic observations by Galileo and others, revealing that other worlds existed beyond Earth, to the space age that allowed us to send robotic emissaries to every planet and many moons. Each discovery has expanded our sense of wonder and our understanding of how planetary systems form and evolve. We have walked on the Moon, landed probes on Venus, Mars, and Titan, flown through the rings of Saturn, and sent spacecraft to the very edge of the Sun's influence and beyond. Yet despite centuries of observation and decades of space exploration, profound mysteries remain. We do not fully understand how the planets formed their moons, why some worlds are geologically active while others are dead, or what conditions are necessary for life to emerge. We do not know if life exists elsewhere in the solar system, hidden in the oceans of Europa or Enceladus, or buried in the Martian soil. We do not know if Planet 9 is real or what surprises await in the distant Oort cloud. Each answer we find raises new questions, pulling us forward in a journey of discovery that seems endless. The solar system is a reminder of our place in the cosmos. We live on a small world orbiting an ordinary star in a quiet neighborhood of an unremarkable galaxy. Yet, this small corner of space contains wonders beyond measure. The delicate balance that allows Earth to harbor life, the violent beauty of Jupiter's storms, the serene rings of Saturn, the hidden oceans beneath icy moons, and the ancient rocks that remember the birth of everything we know. These are not distant abstractions, but part of our home, the larger environment in which Earth exists, bound by gravity to the Sun and to each other. Looking forward, humanity's relationship with the solar system will deepen. Plans are underway to return astronauts to the Moon and eventually send people to Mars. Robotic missions will explore Europa, Titan, and other moons in search of life. New telescopes will search for Planet 9 and catalog thousands more trans-Neptunian objects. Private companies are developing technologies to mine asteroids and establish permanent settlements beyond Earth. The solar system that once seemed impossibly vast and unreachable is slowly becoming accessible, at least to our machines, and perhaps soon to our descendants. But even as we extend our reach, the solar system retains its capacity to surprise us. For the first time, astronomers witnessed the dawn of a new solar system, observing the creation of the first specks of planet-forming material around a baby star called HOPS 315. This discovery allows us to look back at what our own solar system might have looked like in its infancy, a circle completing as we understand our origins by watching similar processes unfold elsewhere in the galaxy. As you lie here in the quiet darkness, your mind drifting through these distant worlds, remember that all of this exists not in imagination but in reality. Right now, as you listen to these words, Voyager 1 and 2 are sailing through interstellar space, carrying messages from Earth into the cosmos. Right now, the Sun is fusing hydrogen into helium, releasing the energy that warms our world. Right now, storms are raging on Jupiter. Ice is sublimating from comet nuclei, and distant trans-Neptunian objects are following their lonely orbits in the cold and dark. All of this is happening simultaneously, a vast interconnected system of motion and gravity, light and shadow, playing out across billions of kilometers of space. The solar system is both a neighborhood and a wilderness, familiar and strange. It is the only star system we can study in detail, the only one where we can send spacecraft to land on alien surfaces and analyze their rocks, where we can measure magnetic fields and atmospheric compositions directly, where we can search for signs of life beyond Earth without traveling to other stars. Every discovery about the solar system teaches us not just about these particular worlds, but about how planetary systems work everywhere. The principles of gravity, thermodynamics, chemistry, and physics that govern the behavior of our sun and planets are universal, applying to the trillions of star systems that fill the galaxy and the universe beyond. So, as we come to the end of this journey, drifting back toward Earth from the cold outer reaches, passing the ice giants and the gas giants, the asteroid belt and the rocky inner worlds, finally arriving home to our blue planet spinning in the darkness. Take a moment to appreciate the improbability and beauty of it all. The solar system is our home on a grander scale, the family of worlds that shares our origins and our future, bound together by the invisible threads of gravity that reach across the emptiness. If you enjoyed this peaceful exploration through our solar system, I invite you to like, subscribe, or share a thought below. Your support helps more curious minds discover these quiet journeys through science and space, one sleepy explorer at a time. For now, let yourself settle. Let the images of distant worlds fade gently into the background of your mind. Let your breathing slow and deepen. Feel the weight of your body relaxing into rest. You have traveled far tonight, across billions of the kilometers, through space and time, from the birth of the solar system to the present moment. But now it is time to return fully to this quiet place, this comfortable darkness, this moment of peace. The planets will continue their eternal dance around the sun, indifferent to whether we watch or not. The storms will rage, the moons will orbit, the comets will sail through the darkness. All of this will be waiting for you tomorrow, and the day after, and for as long as humans look up at the night sky with wonder. But right now, all you need to do is rest. Let your mind grow soft and quiet. Let the solar system fade into dreams. Let the vastness of space become the vastness of sleep. Good night.